Okay, thank you everyone for coming to this second edition of the New Technologies in Mathematics seminar. And so today we're really happy to have Antonio Sclocchi from EPFL. So Antonio has worked a lot on topics like statistical physics, machine learning. In particular, he put out this super cool paper in January about hierarchical data and diffusion models that has really generated a lot of excitement in the community. And so today we're really happy to have him with us talk about this line of work. So Antonio, take it away.
Thank you so much, Hugo, and thank you for the invitation. It's a big pleasure being here. So today I'm going to talk about our recent work on hierarchical data structures and diffusion models. And this is work done at EPFL together with Alessandro Favero and Matteo Diar. So why are we interested in data structure? The reason is that deep learning is actually very successful with high-dimensional data across very different modalities. And we know that in high dimension, probability distributions are hard to sample. So these high-dimensional data to be learnable mean that they must be very structured. And this brings about several questions about what is, when we say the structure of data, what do we mean? So one idea is that of hierarchical compositionality, and it's an idea that we are very interested about because there are actually hints in experimental setting that this can be one key aspect of real data that is actually captured by deep networks. So, for example, what do I mean by hierarchical compositionality? For example, if we look at a deep convolutional neural network that is classifying images, and we look inside the internal layers, what the neurons are most responding to, what we observe is that early layers most respond to simple features like edges or texture and patterns. And as we go deeper and deeper in the network, we see that the neurons respond to more abstract objects like parts of objects or abstract concepts like dog or cat. And so there is this idea that data are actually composed by features that live at different level of abstractions, and the higher level features are composed by lower level features in a compositional and hierarchical manner. So the thing is that this idea is actually very interesting, but the problem is how do we measure it? How do we build a quantitative measure of this idea? And our approach is that of using a generative AI to probe the compositional structure of data. In particular, I'll talk about diffusion models. And these models have shown impressive capabilities in generating data like images or even protein structures. And all these data have in common that they display compositionality at different scales. So, for example, we can think of parsing an image, a face or a celebrity into simpler parts, and the same can be done for other data modalities. And so our goal is basically using the diffusion process to access these compositionality effects in data generation. So the outline of my talk is that I will start with diffusion models, and in particular, I will show experiments on images. Then I show a way of quantifying the compositional effects in these experiments. And then I'll present a theoretical model that is meant to be the simplest theoretical model you can think of to model these compositional effects. And then I'll show some more recent work about probing compositionality in other data modalities. So let me start with diffusion models. What are they? Basically, they are models that have the goal of sampling from an unknown probability distribution. So, for example, you want to sample the image of a dog starting from a probability distribution of dogs' images, but you don't know how to describe this probability distribution. So the idea is that of creating a map that goes from your data space up to a probability distribution that is easier to sample, like, for example, random Gaussian noise. And then what the model has to do is learning to revert this map, such that we will sample the random noise and progressively remove this noise in order to generate a new sample from the starting probability distribution. So this means that these models are made of two processes. One is the forward process that starts from our data x0 and progressively progressively adds noise up to get, for example, to standard Gaussian distribution. And we can think of this process like, for example, a Orsen-Uhlenbeck process that we know that a long time will converge to the Gaussian distribution. And for the backward process, we know from the theory of stochastic differential equation that in order to revert this, in order to run the backward process, we need an additional vector field that is called the score function, and this is time dependent. And so learning the reverse process is basically corresponds to learning the score function. What is the score function is actually the gradient of the log of the probability distribution at times t. And for the considered process that I just showed, that is the Orsen-Uhlenbeck process, you can show that what you need to do is basically estimating the average starting point given that you have a noisy observation at time t. So what happened in recent years is that people understood that with deep networks you can actually estimate this quantity, and if you have this quantity, then you can compute the score. If you can compute the score, you can run the backward process, and in this way you can generate a sample from various probability distributions. So what I want to do in my experiments is playing with the time of the diffusion. So I will use time and noise level in an exchangeable manner, because as you have seen, increasing time in the diffusion process corresponds to adding more noise. And what I will do is using the different noise levels to probe the compositional structure of the images. So I will take a diffusion model that has already been trained on ImageNet, and instead of generating new data from random noise, I will perform a denoising of partially noised data. What do I mean by this is that I take an image, I run the forward process up to time t, so I will have a noisy observation of this image, and then I run the backward process. So in order to sample a new image that is conditioned on this noisy observation. Let me do one example. So here I've added a certain amount of noise to these images, and then I will use the neural network to run the backward process. And what I will get is an image that, as you can see, since the noise I've added is small enough, I managed to reconstruct part of the original image, but I start seeing that the small details are changing. For example, the color of the eyes of the dog, or some details in the head of the dog in the second image. Now, what will be our variable is the diffusion time. And I will call this experiment forward-backward experiments for the reason we have just seen. And if we do, we increase noise systematically and we denoise the images, we observe something like this. Let me explain what you are seeing here. So if I add a small amount of noise, what I'll get back is an image that is basically the starting image, but I see low-level features that are changing. In this case, the color of the eyes of the leopard and some small details of the fur. Then what we observe is that there is a particular noise level beyond which the image basically changes class. So in this case, we get to a wolf. But the very interesting thing is that we still observe that low-level features are conserved. So for example, here we have the ears and the nose of the leopard that arguably are reused in creating this new image. And as I increase noise even more, the class change, the changes in the images are even stronger, but I still observe that small details of the image, like some edges or, for example, here it is black dots, can be overlapped basically with the starting image. So here there is an hint of this compositionality idea, is the fact that I can generate images that belong to different classes, so different abstract concepts, but reusing low-level features like edges or simple geometrical elements. And we observed this very systematically across different images. And for example, here on the bottom row, you can see this car that, again, at the beginning, only low-level features change. But then after the class transition, we see that the armrests of the sofa basically are taken from the lights of the car. So, so again, and it is we can see it across different images. And what we want to do now is actually quantifying these compositional effects, and there is the question on how to do this. So as I show at the beginning of my talk, we know that when we look inside the activations of a deep CNN classifier, we know that early layers respond most often to simple elements of the image, while deeper layers deeper neurons respond to more abstract concepts. So the idea is that I can take the starting image and I can pass it through a deep CNN, and I look at the internal activations of my deep CNN. Then I'll do the same thing with the generated image. And then I can use the internal activations of the neural network as a proxy to see if the low-level features that are those close to the input layers or high-level features that are those closer to the output layer, if these have changed. And what I will do is measure the cosine similarity between these activations. And what we get is something that basically quantifies the phenomenology that I've just described before. So here in red, we see early layers, so layer close to the input, and in purple, we see layers that are close to the output. And again, for time, this is cosine similarity of the activations for different layers with respect to the inversion time t. So what we observe is that at time equals 0, it means that I'm on the same image, so all the cosine similarities are 1, while at the final time, I'm basically sampling another image from random noise, so the cosine similarities are all zeros. And in between, I observe that there is a different behavior between the early layers and deeper layers. So for the red curves, we see that these are the first ones to decrease their similarity. And the reason is because we have seen that at low levels of noise are small details of the image that change. But then this red curve changes smoothly. While instead, when we look at what happens to the logits, for example, these logits are basically conserved for low level of noise, meaning that we are basically going back to the same class, but then there is a certain noise level where there is a sharp drop. And when after this sharp drop, basically we have a random chance of going back to the original image class, while instead we have the conservation of low level features. So the key point in this figure is the crossing of the blue curve with the red curve, and this is what we call the compositionality effect. So when we want to build a theoretical model of this compositionality, what we aim to reproduce is exactly this crossing between the conservation of low-level features with respect to that of high-level feature. So I proceed with the theoretical model. Are there questions up to now? Okay. So the question is which kind of model can we use to reproduce these compositionality effects? And of course, we need some model that displays compositionality and hopefully hierarchical compositionality. And we have some the people already thought about this kind of problem, and in particular, there are interesting hints from the field of linguistics and formal grammars, where basically hierarchical models have been used to model the structure of the syntax of languages. Then later on, these ideas have been transferred also to computer vision, where again it's pattern theory that tried to formalize this parsing of images through features that live at different levels of abstraction. And for our purpose, what we want to do is basically take a simple model that is organized on a tree graph, such that the root corresponds to the most abstract feature, that is the class, while the leaves corresponds to the low-level features. And there are production rules that connect these features inside the internal layers. And this model has been introduced by my colleague, that is the random hierarchy model. The idea is that of taking a regular tree graph with a depth L and branching factor S, we will have discrete symbols for each node of the tree, and that will belong to a vocabulary that has a size V. And I will have production rules that are chosen randomly and all distinct, connecting these symbols. And I will have another parameter that we call M, that is the number of synonyms between the representation from a higher level feature to lower level feature. Let me do an example to be more concrete. For example, here we have a tree of depth 3, branching factor 2, and I have 3 possible symbols for each layer. And I have a number of synonymic production rules, that is 3. So for example, I start from class 1. I can choose between 3 possible lower level representation. For example, I can choose A, B, and I put this in the corresponding children nodes. Then again, from a feature A at this level, I can choose between 3 possible production rules, and I can choose, for example, EF. And again, I iterate this process. What we observe, first of all, is that these rules, we chose them to be random, and we choose them to be all distinct. So if I have AB to represent class 1, I cannot reuse this rule to represent other classes. And then you can also see that the symbols are reused to create different rules. So in this sense, we have a compositionality of features that are composed in different manners to create different higher level meanings. And what we get at the end of this generative process is a string that has a size branching factor power the depth of the tree, and it constitutes our input data. So one interesting aspect of this generative model is that it's defined on a tree graph, and this is useful if we want to study, for example, a diffusion process, because we know that on tree graph we can use message passing algorithm, and so when I run the diffusion backward diffusion process, I can perform the denoising using belief propagation. Of course, I'm assuming that I already know the rules. So if you want, it's like if I have access to a neural network that has perfect generalization on the backward diffusion process of this model. And how does it work, this algorithm? So we start from, we have the rules that are known, and this creates factor nodes that connect lower level feature to higher level feature. And the way that belief propagation works is that you start with the priors at the leaf of your tree, and you use the this iterative procedure to compute the higher level messages. And you iterate this process upward, up to the root. Once you are at the root, you can propagate the messages downward, basically using the same equations. And at the end of this process, what you end up is basically, for this specific tree, you end up with upward messages and downward messages, and the marginal probability on the value of each latent node, it can be computed from these messages. So here I make an example where the noisy observation, so that if you want, it's the forward diffusion process. It's basically giving me these prior messages at the leaves. These get propagated upward, and then once I reach the root, I can propagate them downward. And so from the product of these two messages, I can compute what's the marginal probability of each node, given that I have a noisy observation at the leaves. So this is the way we can perform experiments with forward-backward diffusion in the random hierarchy model. And here, let me introduce a simplified version of the diffusion process. What I will do is, instead of using the time t, I will use directly a noise-to-signal ratio. This is, I will call it epsilon, and if you want to map it to the time of the diffusion, is basically creating a mapping between time and noise. And what I will do is basically I'll take the prior at the leaves and I will decrease it by epsilon on the symbol that corresponds to the starting symbol of my datum. While instead, as epsilon increase, I will increase the probability mass that I have on the other values of my leaf node. So to make an example, let's say that I have this starting datum that are my visible nodes that has been generated by this latent tree. Now, what I do is, for example, for the first node that had value I will decrease prior according to the value of noise I want to inject in my data. So now we'll have a prior that is 0.8 for the symbol I, and I have some probability on the other symbol. And then starting from these leaf priors, I can run a belief propagation that is simply the algorithm we have discussed before. And as a result, what we get is the probability for the values of each latent node. So you see where I'm getting to is what we want to compute is given a certain noise level, what's the probability I can reconstruct the original value of some latent node of my datum. And here are some results. So here I'm showing on the y-axis the probability of reconstructing the node. I'm using colors to indicate the different levels of the hierarchical tree, and I'm using the same color code as before. So we have for red the early layers that corresponds to the leaves, and in purple we have the root node that corresponds to the class, and on the x-axis we have the noise scale. And what we observe is basically a phenomenology very similar to what I showed you before for images. So for the root, we see that the reconstruction probability has a sharp transition where it goes from being 1 down to basically being random chance. Instead, if we look at low-level features, these are the first one to decrease, but then they cross the purple curve and are those who persist the longest, also at very large noise levels. This means that after the class transition, we are in a situation where our datum goes back to a datum of a different class, but it's reusing some low-level feature of the starting datum. You can complain that now I'm doing this looking at the BP probabilities, while instead for images I've done it using a CNN classifier. And what we can do is basically run the same experiment. So here I've trained a CNN classifier to classify the data of the random hierarchy model. And here I look at the cosine similarity between the starting datum and a datum that has been generated by the forward backward experiment. And again, we see basically the same phenomenology where the logits are those who have a sharp decay. The cosine similarity of the logits are those who have a sharp decay, while instead the early layers are the first one to decrease and then they cross the purple curve. And again, this is something that has some resemblance to the ImageNet phenomenology I showed you before. Let me say something more about the theory that we can study for this hierarchical model. As I said, I'm using this simplified epsilon process where I decrease the prior at my leaves, at my leaf priors. And what I can do is when I propagate the message upward, I can perform what I will call a mean field theory of this process. What I mean by mean field means that I'm basically taking all the messages at a given layer and I'm basically just computing their average. So what I'm doing here is basically averaging over the realization of the random rules of the random hierarchy model. And because of the symmetry of the problem, what I can observe is that as I go from one layer to the upper layer, what I get is a message that have the same form as before. So they are basically 1 minus epsilon for the correct value of the node, and they are epsilon over v for all the other values. But basically the noise has been renormalized to a new noise that is epsilon prime. So basically, we have a sort of a renormalization map on the belief that we have on the correct value of the node. And we can compute this function f, that is our iterative function that basically maps the noise level from one layer to the other. And we can study the fixed point of this map when we go to the limit of infinite layers. Let me show what happens. Basically, we get an iterative map that that depends on the parameters of the random hierarchy model. So, for example, here you can see the appearance of S, that is a branching factor. You see the appearance of V, that is the vocabulary size, and then you have this parameter F, that is basically a sparsity parameter, means that is the ratio between the number of synonyms in the production rules divided the space of strings that I can possibly generate, such that for small f, it means that my generative model is just sampling a very small subset of the possible strings. Instead, for large f, it means that I'm basically sampling all possible strings. And this is interesting because according to f, we see that the fixed point of this iterative map change. So we go from a situation where we have just two fixed points, that is p equals 0 and p equals 1, that correspond to perfect reconstruction or random chance. And for a smaller f, what happens is that a third fixed point appears, and this third fixed point is repulsive and corresponds to the phase transition in the class that I talked about before. And so, for example, here you can see a phase diagram of with respect to the noise level and this parameter f. And we have two regions, the inference region where we can reconstruct the class of our datum, and the no inference where we cannot reconstruct the class. And what I was showing you before is basically a cut in this phase diagram where we were crossing this transition line that we can compute very effectively using this mean field approach. So actually, what I showed you before is what happens when I compute the average messages, iterating them upwards. I can do the same thing when I run the downward iteration of belief propagation. And when you solve it numerically, what you obtain is basically you can reconstruct what's the average probability of reconstructing a node. And here you can see that at every layer, here I'm showing only layer 0 and layer 10, basically this mean field theory actually captures the behavior of the BP experiments that we run on this model. So are there questions up to here? Okay. So up to now, I've shown you experiments with the diffusion models where basically we try to access the latent hierarchical structure or directly in the case of the random hierarchy model where we can access to the generative tree, or through a proxy that was the internal activations of a deep convolutional neural network. But in general, it's not easy to access this latent structure. And an interesting question is, can I look at the the effects of latent structure if I just look at the input space? So if you want, at real space. So for example, I only have my starting image and the newly generated image, and can understand if there are compositional effects only looking at what happened to the image. So this is recent work with Alessandro Favero, Nom Levi, and Mathieu Viard, and is going to appear soon on the archive. And what we are doing here is basically always the forward-backward experiments I talked about before. But now what we are interested in is looking at which parts of our data are changing. So let me make an example, and here I'm considering what is called masking diffusion, where basically the token, if you want, the symbol of my random hierarchy model are masked, and then the noise, basically, always using belief propagation. You can see visually already that the starting datum x0 has some masked symbols that are the blue and the green symbols. And then when I run the backward process, I generate a new datum where the masked symbol eventually have changed or not. But these changes what happens that these changes reflect some changes deeper in the hierarchical tree. So here in red, I'm showing symbols that have changed between the generative tree of the datum x0 and the generative tree of the new sample datum x0 hat. And we can see that as we mask different fraction of our datum, what happens is that we can change deeper and deeper symbols inside our latent tree. And so what happens is that if I'm changing some very deep latent symbol in my tree, what should happen is that because of the generative rules, the changes in the input datum should be correlated. So for example, I can expect that when I change the class, I'll generate basically a cascade of changes in my tree that will correlate my changes at a very long distance. So you can see where this reasoning is going to is basically that we can define a binary variable that is, for example, in this case, a spin that is associated to each symbol of, if you want, each token of my input datum, and this spin variable is +1 if I've changed the symbol of that token, and is equal to -1 if this symbol has been conserved. And now that I have this spin chain, I can basically compute its correlation function that it will depend on the relative position of my spins. And here the bracket corresponds to the average over different noisy trajectory forward backward of my diffusion. Now this is done starting from a certain datum at 0, and then I can compute the average correlation function by averaging over all possible starting datum data. And once I have a correlation function, I can define a susceptibility that is simply the integral of this correlation function. And now let me show what happens if I run this experiment on the random hierarchy model. So here I'm using masking diffusion, and on the left plot you can see again the probability of reconstructing a node. I'm using the same color code, so layer 0 are the leaf nodes, and layer 10 in purple is the root node. And again, you can see that the root node is undergoing a sharp transition, while the probability of reconstructing leaf nodes is changing smoothly and is crossing the purple curve. Now, we observe that there is a phase transition around the masking fraction that is 0.3. And here I'm on the central plot, I'm showing the average correlation function that I defined before between the changes in my tokens for different level of inversion time of the masking and the noising process. And again, we see that for inversion time that is around 0.3, we have a power, the red curve is basically a power law decay of our correlation function, while for other noise levels, we see that the correlation function decays sharper, it decays faster, and defines some correlation length that is maximal at the phase transition that corresponds to T0.3. And in correspondence of this phase transition, we can see that the susceptibility also shows a peak. And this is really consistent with what we see on the correlation. Let me do the same experiment for text, for example. And what we observe is basically a very similar phenomenology. In this case, we have the original sentence where some words get masked progressively as we increase this forward diffusion time. And then when we go backward, these words can change or eventually stay the same. And then what we measure again is the correlation between changes in the newly generated sentence. And again, we see that there is the correlation function displays different correlation length, and this correlation length is maximal for a specific noise level that in this case is around 0.5 or 0.6 of the final time. And again, if we compute the susceptibility, we see that it shows a peak around this maximal value of the correlation length. We can do the same thing also for images, but now we have the problem that we need to define some meaningful token for the image. And to do that, what we use is basically a tokenizer. We use the vision encoder that has been trained to represent the semantics of the image. And in this case, we use the vision encoder of the clip model. And here I'm showing the starting image and then the generated image with the forward-backward diffusion. And with the grid, I'm showing the different tokens. And in red, I'm showing tokens that have changed more than a certain threshold value. And you see that as new semantic elements in the image appear, we see that blocks of tokens that change together. And they create these large patches of tokens that change. And once we have these token changes, we can measure the correlation function. Also in this case, and again, we see here that we have a certain value of inversion time that corresponds to a correlation function that shows a power law decay. And this happens for inversion time around 0.6, 0.7, that was exactly the last level where we observed the class phase transition for ImageNet. And again, consistently, the susceptibility also shows up in correspondence of this phase transition. So up to now, I've run experiments using trained diffusion models or belief propagation for our random hierarchy model that implies that we already know the rules. And so therefore, there are interesting questions about what happens if I don't know the generative rules and instead I want to learn to denoise the data using a neural network. And in this regard, we have some interesting ongoing work that of using UNet to denoise random hierarchy model data. And the reason why it is interesting is because when we look at the UNet structure that is made of an encoder and decoder structure that are connected with the long residual connections, it very much resembles the structure of the belief propagation algorithm, where we have the upward process that somehow plays the role of the encoder and the downward process that plays the role of the decoder. And in the downward process, we have the reuse of the upward messages that somehow corresponds to this long residual connection. And there has been some interesting work showing that actually UNet can efficiently approximate the belief propagation algorithm. So our question is, on this hierarchical data, if we train the UNet, do they learn with the gradient descent, do they learn the belief propagation algorithm or not? So to conclude, what we have done is we probed the compositional effects in images and text using diffusion models. And then we show that these effects can be understood through a simple hierarchical generative model. And this opens very interesting questions, as I said, about learnability and sample complexity for diffusion models, and also about how much universal are these phenomena, and if they appear also for other data modalities, like, for example, diffusion models on proteins or other data structures. And with this, I thank you.
Thank you very much, Antonio. Yes, are there any questions in the audience from Zoom?
Yeah. Sorry.
If not, I have one like a very high level question. Do you have any intuition why the lower level features subsist while the higher level kind of undergo this phase transition? Because naively, I would expect maybe my intuition would be that the lower level features would be like the small details that would be kind of lost to noise before the higher level features. And I kind of find it counterintuitive that those ones are kind of what remain. I don't know if you have some intuition to give us.
Yeah, this is a very good point, meaning that that's what one would expect, that if you lose information on a very complicated structure at a large scale, why should you retain information on small details? And actually, I don't have an intuitive answer. So for the case of belief propagation, I see it through the messages, because the low-level features are the closest to the input messages at the leaves. So they have some like information that is not lost in the propagation of the upward messages. But instead, that's what happens when you go to the deeper layers. But then why it is the case in real data, I don't know.
I see. Thank you.
Can I ask a little more detail? So the model you had in the middle of your analysis with the RHM, so that's an idealization of the diffusion model, right? Where you're putting in the noise in a different way, not literally diffusion, but it's still noise, right?
Yeah, sorry, I cannot hear very well.
Your RHM analysis is I mean, it's related to you. So you started your talk with the example of the diffusion model and images, and then your RHM kind of toy model of that is an analog. It's not really diffusion, right? It's introducing noise, which models the noise that diffusion would introduce, right?
Yes, so in this case, I presented the simplified process. You are right, because on that it's easy to make theory. But we can also run the proper diffusion process, and we observe that the curves are the same.
Would
So,
the diffusion be on the input, or would it be on the latent variables as well? So I mean, I guess the original definition, the diffusion just acts on the input.
yes, diffusion is only on the input. It's not on the latent.
It was also the case in your RHM. The diffusion was just on.
Yes. Yes.
Okay,
yes.
So I mean, there's some sense in which you could think of your phase transition as amplifying. I mean, it's just like you said, it's a fixed point. And so at a fixed point, you have an
exactly
amplify.
It's exactly that.
Right.
Basically, the meaning of this fixed point is if you have an error at the leaf, does it propagate or not? Does it get corrected? Does it iterate the equations or not? Yes.
So in that sense, the noise always starts out at the low level, but because the high levels are combined, the result of combining low level things, that's at least to the potential of amplification. And then when you pass the transition, it does amplify. So that's
exactly
sort of the answer to why the low level features can be preserved and the higher level features can change suddenly. Is that process of amplifying that original noise?
Yes, exactly.
It's very interesting. It's a much more accessible model and a lot of things you say.
Marvin has a question on Zoom.
Yeah. Can you hear me?
Yes.
Yeah. So I guess just very interesting talk. I've done work on this project on this kind of question as well. Like we worked on proving where these kind of we call these critical windows where they would occur in the sampling procedure. I'm just curious, what are your thoughts on how do you I guess what are your thoughts on where these how you would define a feature, or how these in some how do you conceptualize a feature, at least beyond your model, or how, in the application of your random hierarchy model to real data?
Yeah, this is very good question. So in the case of grammar, this is or in the case of formal grammars, this is actually done where you basically these are constructed in a way to model realistic grammars. For the case of images, I don't think that that is possible to build univocally a hierarchical tree that represent the semantics of the image. I don't know how is it if it's even possible to think of fitting the random hierarchy model to some data. But for sure, what we can do is predict what happens to some observable real space correlation and these kind of things, and see what's the effect of having a hierarchy of features with respect to not having a hierarchy of features. So yeah. So in this sense, is still an abstraction of real features. Then how to define real features for real data is I don't know. I don't have an answer for that.
Yeah. I guess what we kind of did is that we would basically something remains. We kind of define things in terms of the total variation distance between at different points in the noising procedure, and we said at the point two features are kind of distinct if you're able to add noise and for them to still kind of be discerned from each other. I guess another question I had is that if you look at the score function itself of a diffusion model, and you look at the score function for a mixture model, so if you assume that the data is drawn from some mixture, it decomposes really nicely in the sense that it ends up being a weighted combination of the score functions of each of the components times some sort of weighted conditional probability that belongs to this cluster or this cluster at that time t. I'm just curious if like in your kind of calculations with this, whether you saw something similar in the sense that like there are some coefficients that correspond to like the belief that belongs to different like to different categories.
That is not the case because the problem is that for the data for this random hierarchy model data, basically the roots are random. So it means that as soon as you change one feature, the meaning of the string can be whatever. So so you don't have the case like you have for a Gaussian mixture, for example, where nearby data have the same meaning. So if you want your score function, if it's bringing towards one of the class, then it's like aggregating points towards the Gaussian that represent that class. Instead, in the random hierarchy model, you don't have that. You have like different random strings, and different random strings mean different things.
Thank you so much. Wonderful talk.
Thank you.
Have you studied just straight generate data with the RHM and learn to classify it with FNN and try to figure out how it works?
Trying to classify with the DeepNet?
Yeah, just generate with the RHM so you know the structure and then
Yeah.
and presumably it can figure out how it learned it.
Yeah, so that is done by my colleagues who studied the supervised learning for this model, and then they looked inside the DeepNet what is learned, and they show that the depth is helping you learn in the hierarchy, and you cannot do that with a shallow network.
Okay, so there's some kind of answer to the question of what are the features that it learned, right? Because you put the features in and it did learn them, right?
Yeah, it's a good question. What happens in that case is that basically layers learn to put together synonymic patches. So basically, patches that have the same meaning basically get mapped to the same internal activations. And in that way, if you want, you reconstruct the hierarchy layer by layer. Now, this you can measure if you take like a DeepNet that is matched to the parameters of the random hierarchy model. But then, of course, you can say, okay, let me take a much deeper network, and then you cannot make a one-to-one mapping between the layers of the model and the network. And and then it's a good question, like which feature does the network learns?
Do we have any more questions? If not, thank your speaker again.
Thank you.
Thank you so much.